In this video I want to do a couple examples. The first example I want to do is I want to do an example of showing what a field is. So the real numbers are a field. And that's going to be kind of our easy example. And we'll just go through it real quick, and then we'll do something a little bit more difficult to show an example of a field and what you would have to do to actually show something's a field. So the real numbers are a field because we have addition and addition and multiplication, and we've got some axioms for each of those. Addition has closed. It has commutative property. It has the associative property. It has an identity. And it has inverses. Multiplication has the same things. It's closed. It's commutative. It's associative. It has an identity. And it has inverses. And then we've got the distributive property, which shows how addition and multiplication interact with each other. Okay. So it's closed. Any two real numbers added together also is real. Commutative, x plus y equals y plus x. Associative, x plus y plus z. If I do y plus z first, that's equal to if I would have done x and y first. The identity is 0. 0 plus a number equals the number. And inverses, x plus negative x equals 0. Right. Multiplicative, we've got closed. Any two reals multiplied together is real again. Commutative, x times y equals y times x. Associative, x times y times z. If I do y and z first, that's the same thing as x times y times z. Our identity with multiplication is 1. 1 times x equals x. And our inverse is x times 1 over x. 1 over x is the inverse, also sometimes written as x times x inverse, and that's equal to the identity. And the distributive property, a times b plus c is equal to a times b plus a times c. Okay. So that's an example of what makes the real numbers a field. So let's see where things go wrong if I change to, for example, the integers. Okay, so let's look at z. If I take any two integers added together, I still get an integer, so that's good. Commutative, that works out. If you add two integers, you can add them in any order. Associative property works out. 0 is an integer. It's an identity. If I take 0 plus any integer, I still get 0, or I get that integer. Inverses, I have In the integers, I have x and I have negative x, and if I add x plus negative x, I get 0. That's good. Okay, so far it looks like the integers might be a field. Let's check out multiplication. I've got two integers multiplied together, it's still an integer. If I take the commutative property of integers, multiplication works. Associative property, multiplication still works. 1 is an integer, it's still the identity. So these guys all work. Oh wait, I don't have inverses with integers. This fails. Distributive property works too. So the integers are almost a field, I just don't have inverses, right? Okay. If I include the inverses for the integers, what do I end up with? Well, I end up with like 1 over 3 and 1 over 7, and I have to add all multiples of 1 over 3 and 1 over 7 and 1 over 3 billion and stuff like that. So I end up with the rationals. The rationals are a field too. Okay. In some sense, they're the smallest field because that at least contains the integers, because they're exactly what needs to be in there. The integers work for everything except for inverses. If I include the inverses, I get the rationals. Okay. So let's see another example of a field, and this will be a little bit unusual. So let's look at F, and what it's going to be the set of a plus b times the square root of 2, where a and b are rational numbers. Okay, let's prove that this is a field. For me to show that this is a field, I need to define addition, and I need to define multiplication. Well, these are real numbers that we're working with, so I can use just the addition and multiplication from the real numbers. However, just like the integers, I have to show that inverses are there and all that stuff. Okay? So, with addition and multiplication inherited from the reals. Okay, so let's show the addition stuff first. Is it closed? Well, a plus b times the square root of 2 plus c plus d times the square root of 2. I've taken a number from the field and another number from the field. I've added them together. I need to show that it's still a number from the field. Well, I get a plus c plus b plus d square roots of 2. And here I've used commutative property and associative property and the distributive property sort of implicitly, but I think we're probably comfortable with those. And this is also in the field. So we've got closed, checks out. Commutative property, that's inherited from the addition of the reals too. Since it was commutative in the reals, it's commutative in this smaller set. Same thing with associative. Okay, what about identities? 0 is equal to 0 plus 0 square roots of 2, which is in the field. And this is our identity. And since 0 plus a plus b squared roots of 2 is equal to a plus b squared roots of 2. And then what about additive inverses? Well, a plus b squared roots of 2 plus negative a plus negative b squared roots of 2 equals 0, and this is also in the field. So inverses checks out. Okay. Addition wasn't so bad. Multiplication. Is it closed? Well, now I have to take two numbers from this set and show that if I multiply them together, I end up with another number from the set. It's not quite as obvious as with addition, where I could just add the components. So I have to actually show the multiplication works out. A plus b squared roots of 2 times c plus d squared roots of 2. Well, if I FOIL this, I get a times c plus a times d squared roots of 2 plus c times b squared roots of 2 plus I get b times d times the square root of 2 times the square root of 2, or 2bd, which is a times c plus 2bd, rearranging things, plus ad plus bc square roots of 2. This is rational and this is rational, so this is back in the field. So closure works out fine. Commutative property and associative property, these are inherited from the reals. Since it was true in the reals, it's true in this smaller set. And then identity, well, I need a 1, and that's equal to 1 plus 0 square roots of 2. And that works out fine. Now inverse. Remember, this is the hard one. This is the one that caused the rationals not to be a field, or the integers not to be a field. To make it a field, we had to go up to the rationals. So this is kind of the hard one here as well. I need to find an inverse. I need to find, we need c plus d squared roots of 2, so that a plus b squared roots of 2 times c plus d squared roots of 2 is equal to 1, as long as both a and b aren't 0. As long as both a and b are not. Right? If they're both 0, I've got 0, and I can't find an inverse for 0. That's fine. So let's look at our multiplication. Right? We performed the multiplication for the closure, so now I can use that multiplication with this and try and figure out two inequality, or a system and two unknowns that I can solve to get the solution. So I need a times c plus 2b times d equal to 1, and at the same time I need a times, let me put them in the right order, a times d plus b times c equal to 0. Right? This comes straight from up here, because I want this to equal 1. I get these two statements. Okay, so I've got a system and two unknowns. My unknowns are these guys. Okay, that's not a very good color. My unknowns are C and D. Because I'm given an A and B, I need to find the inverse for A plus B squared roots of 2. I need to figure out what C and D are. Okay, so these are my unknowns. Okay. We can solve systems of 2 unknowns and 2 equations. So let's try and do that. I'm going to use Kramer's rule because that's kind of the easiest one in this situation instead of doing a lot of algebra. So by Kramer's rule, which says I've got the determinant of, well, my coefficient matrix is A, 2B, B, A is equal to A squared minus 2B squared. Okay. And this is non-zero no matter which rationals A and B I have, right? This is non-zero since A and B have to be rational numbers. Otherwise I'd have sort of a square root of 2 being rational. So this is a non-zero. And then what I have is C is going to be the determinant of, well, I replace A, B with 1, 0. And I divide it by this A squared minus 2B squared, which is going to be A minus 2B, nope, A 0 times 2b is 0 over A squared minus 2b squared, and D is equal to the determinant of, well, if I replace the other column by 1, 0, get A, B, 1, 0 over A squared minus 2b squared, which is going to be negative B over A squared minus 2b squared. So the inverse together, A plus B squared roots of 2 inverse is equal to A over A squared minus 2B squared plus minus B over A squared minus 2B squared square roots of 2. So there's my inverse. This is in F again. Because this is rational and this is rational. These are both rational. Okay, so that shows that we have inverses inside this set. The last thing to show is the distributive property, but the distributive property is inherited as well. Okay, so the set A plus B squared roots of 2, where A and B are rational, is a field.